Hey guys, so today we will be covering half-life. Half-life, it says at the top, is defined as the amount of time it takes a given quantity to decrease to half of its initial value. So if I have one half-life and I started with one, then now I'm at a half. If I go another half-life, now I'm having that half, so I'm at a fourth. So each time it's going to go one half more, one half more, one half more. And so we use these a lot with science. And so we'll see that kind of with the practices that we're doing a lot of like different types of fossilized things or elements and things like that. So we're describing decay. We're getting smaller and smaller and smaller every time. The notes here do show you how to do it with a negative exponent, and then they do go on to do their example with that negative exponent. I do prefer this one, or you may see me write it as n. So it's the same thing with the initial amount having that little zero there that's called naught. So a naught, and then we've got a. So I'm going to jump straight into the practice problems. I'm not going to go over the practice problem that is there on the first page, just because she uses the different exponent. So we can use a of t. We've got a naught, so the initial amount, and then we have 1/2 to the power of t over h, where t is our time and h is our half-life. So the half-life of CS137, it's going to be an element, is 30.2 years. If the initial mass of the sample is 1 kilogram, how much will remain after 151 years? So we've got our our end amount is what we're looking for. So how much will remain? We're looking for end amount. So that means we have to have everything else. Our initial amount is 1. Then we'll always have 1/2 since we're dealing with half-life. T is the amount of time that is passing. And h is the half-life of whatever we're working with. And then whenever we're finding the end amount, we can just plug that straight into the calculator exactly as we have it written. Don't try to solve anything or simplify, just type that straight in, because it is going to be something a little crazy. It's going to give you a decimal for sure. So just give me a second as I type this in. If you have your calculator, type it into yours as well. So we get 0.0131125. And since our starting amount was in kilograms, and we're finding our end amount, it is going to be in kilograms as well. So if we start with 1 kilogram of this element, after 151 years, we will only have 0.013 kilograms. On number 2, carbon-14 has a half-life of 5,730 years. Consider a sample of fossilized wood that, when alive, would have contained 24 grams of C14, which is carbon-14. It now contains 1.5 grams. How old is the sample? So we're trying to figure out how much time has passed. So we have got, let's write out our formula. So our ending amount is 1.5. Our initial amount was 24. 1/2. We're trying to find t, and the half-life is 5,730. Now, whenever we're dealing with a half-life that we're not just finding the end amount, we will have to do some moving around first. I'm going to divide this side by 24 and this side as well. I get 0.0625 is equal to 1/2 to the power of t over 5,730. Now that we have an exponent, a base to an exponent equal to a number, we can convert it to a log. That way we can solve what that t value is. So we have log base 1/2 of 0.0625 is equal to t over 5,730. So let's find what that log value is. I'm going to put that in my calculator. It's 4. So 4 equals t over 5,730. And then we will multiply by 5,730 in order to get t by itself. And we get 22,920 is equal to t. So this is in years. So that fossil would be 22,920 years old if it had 1.5 grams still left of carbon-14. On number 3, a 64-gram sample of germanium 66 is left undisturbed for 12.5 hours. At the end of that period, only 2.0 grams remain. What is the half-life? So this is what we're looking for of that material. So we start with 64 grams for 12.5 hours, and then we have 2 grams remaining. So I'm going to write our formula again. And we're looking for the half-life, so we're looking for H. So we've got our end amount is 2.0. Our initial amount is 64. 1/2. Time is 12.5. And then we don't know H. So again, we have one where we have to move things around first. We're going to divide everything by 64. We get 0.03125 is equal to 1/2 to the power of 12.5 over H. Now that we have a base with an exponent alone, we can convert. So this is log of 1/2 of 0.3125, sorry. And that equals 12.5 over H. So now we need to get H by itself. So what I'm going to do is multiply by H. So I get H log base 0.5 of 0.03125 is equal to 12.5. Again, I want H by itself. So now I'm going to divide by this whole log. So then I get H is equal to 12.5 divided by that log. Log base 1/2 0.03125. And that's going to be my hours for the half-life. So we'll put that into our calculator. And we get 2.5 as our answer. So the half-life is 2.5 hours. On number 4, with a half-life of 28.8 years, how long will it take 1 gram of strontium-90 to decay to 125 milligrams? So we do have to be careful here because this is 1 gram and this is 125 milligrams. So we are going to convert to be the same. So this is 1,000 grams. I'm going to rewrite my formula. And so this is how long, so I'm looking for time. My initial amount, well, my end amount is 125. My initial amount is 1,000 milligrams, sorry. One half to the power of t over the half-life of 28.8. So I'm going to divide by 1,000 first, so I can get the exponential by itself. 0.125 is equal to 1 half to the power of t over 28.8. Then I'll convert. Log base 1 half of 1.125 is equal to t over 28.8. And that would be 28.8 log 0.5.125 equal to t. So then we can put that whole thing into our calculator. And we get that our time would be 86.4, and our half-life was in years, so 86.4 years. So pay attention to your units. Since my units were in years, my time was in years, then I'm going to end up with my answer in years. Since I had grams and milligrams, I did have to change it so that they matched. Number 5, CO60 has a half-life of 5.3 years. If a pellet that has been in storage for 26.5 years contains 14.5 grams of CO60, how much of this radioisotope was present when the pellet was put in the storage? So we're trying to find the initial amount. We have a half-life of 5.3 years. It's been in there for 26.5 years, and it now has 14.5 grams. So we want to find A of t. Sorry, we want to find A naught. We have A of t. A of t is the amount we have now, which is 14.5. We don't have A naught. And then our t is 26.5, and our half-life is 5.3. So we're going to go ahead and put this into the calculator. We're taking 1 half to the power of 26.5 divided by 5.3. So that gives me 14.5 equals A naught times 0.03125. And then to get my initial amount by itself, I'll divide out that decimal. We get 464 as A naught, and our unit would be grams. So there are 464 grams of CO60 when they initially put the pellet in the storage. On number 6, a 1 kilogram block of phosphorus 32, which has a half-life of 14.3 days, is stored for 100.1 days. At the end of this period, how much phosphorus 32 remains? So this question is asking me for the end amount. So our end amount is what we're looking for. Our initial amount is 1 kilogram. Our time is 101 days, and our half-life is also in days. So our half-life and our time do have to match. So we were working with years before, but now they both say days, so we're good. If one said days, one said years, we would have to convert. Since we're finding the end amount, we can just put this straight into the calculator exactly as we see it. We don't have to move anything around. And we get our end amount as 0.0078125, and that is in kilograms. And that was just from putting that whole thing in the calculator as it is. Number 7, radon has a half-life of 3.8 days. After 7.6 days, so they do match, 6.5 grams remain. What was the mass of the original sample? So we're looking for A naught. So we have the amount after, so 6.5 grams. We're looking for A naught, go 1/2. And then we have the time as 7.6 days and our half-life as 3.8 days. So we'll put this into the calculator. And we get 0.25. So now we have 6.5 equals A sub naught. So now we'll divide by 0.25. And we get 26. So 26 is our initial amount, and that will be in grams. So then these are all the problems that I'm going to do, which leaves you 10 problems to do. I did work every single type. So when you're looking for the time, when you're looking for the half-life, when you're looking for the initial amount or the end amount, so make sure that you are aware of what you're looking for before you begin the problem, so that way you know what's the unknown in your formula. If you do prefer to use the other formula that is here, that's okay. But I do prefer to use the first one, so that's why I did the first one on all of the notes. So that is all for the notes. Make sure that you get this turned in, and then I'll see you in the next one.